Hello everyone, in this video we'll be solving problem 230, kth smallest element in a binary search tree. The problem statement is, given a root of a binary search tree and an integer k, return the kth smallest value, one index, of all of the values of the nodes in the tree. In example number 1, there are total of 4 nodes in the tree and the k value is given as 1. So we need to return the smallest number in the node, which is node 1. Similarly, in example number 2, with this binary search tree and k as 3, the output is this node 3 because it is the third smallest number in the entire binary search tree. This is a very easy problem and I'm sure it will not take too much time to understand how we can solve it. Let's switch to whiteboard and discuss couple of approaches. The simplest approach is the brute force approach, where we'll iterate through all of the nodes in the given binary search tree, record all of the values in the collection, then sort the array to make sure all of the elements are in ascending order, and then take the kth element. If we were to take this approach and solve this problem, after traversing through all of these nodes and recording its value, my array would look something like this. For traversing, I haven't used any particular technique here because we are anyways going to sort it later on. After sorting this array, the updated array would look something like this. Now we can easily identify the kth element from this array. Because it is one index, we'll do k minus 1, so the output is 3. With this solution, our time complexity is O of n plus O of n log n. The n is because we are iterating through all of the nodes in the given array, and the n log n is because we are sorting the array in the ascending order. While the space complexity is O of n, as we are maintaining this array with all of the nodes. Although this solution works, there is a way we can improve our time complexity. So now let's think about how we can optimize our solution. The optimized way to solve this problem is to use the properties of a binary search tree and then use in-order traversal. In a binary search tree, the value of the left node is always going to be less than the root node, and the value of the root node is always going to be less than the right node. And if we use the in-order traversal, we first process the left node, followed by the root node, and then the right node. Now let's say there are a total of 3 nodes available to us and our k is given as 2. If we go by the in-order traversal, my first node that will be processed is the left node, following that will be the root node and the right node. And because it is a binary search tree, in-order traversal will make sure that all of the nodes that we have processed are in ascending order. We don't need to apply any sorting on top of it. And with k is equal to 2, the second element that was added to the collection or that was processed is already the second smallest number in the entire collection. So we'll use these two combinations to solve the problem. Let's understand this better by simulating this in the given example. We'll use a variable vals to maintain all of the nodes that we have processed. In the in-order traversal, we'll start the traversal from the root node and dive deeper all the way to the leftmost node of it, which is node 1, and we'll add it to the value. After adding it, we'll check if value.length is equal to k. If the value is not equal to k, it means we still need to process few more nodes to get to that point. After processing node 1, we'll go to its parent node, that is node 2. We'll add it to the collection again. The array size is still not equal to k, so we'll continue forward. So now we'll traverse from 2 to its right node or right leg, which is node 3. Similar to previous operation, we'll add it to the values variable. Now we'll check the condition again. This time the condition is sufficed, which means we have already identified the lowest 3 or lowest k elements in the node. So we'll stop the traversal here and return the last element that was processed, that is node 3 as our output. Because we have already figured out our output, there is no point in traversing further. So we don't need to process node 4, 5 or any other nodes that could be there on the right side of the root node. With this solution, our time complexity is improved to O of n, where n is the number of nodes. In the worst case scenario, and we will have to process all of the nodes in the given binary search tree. But in a good case, we will only have to process a total of k nodes. And the space complexity is also similar to time. In the worst case scenario, it will be O of m. But in a good case, it will be of size k. I hope you were able to understand this explanation. Let me show you how we can implement this using C Sharp. Here is the C Sharp solution. Instead of using the list, I am using a stack of type int to keep tabs on all of the nodes that we have processed. I'm then calling this helper method DFS, which will help me iterate through all of the nodes using in order traversal. In the DFS method, I am accepting the current node, the value of k, and the stack collection. If the node is not null, then I'm recursively calling the method again, passing the left node so that we can go all the way to the left side of the tree. If the size of the stack is less than k, then I'm pushing the current node into the stack and then calling the DFS method again, but this time I'm passing the right node. The recursion call will stop once this condition is not sufficed, and I am returning the last element that was added to the stack in the main method. This code, when submitted on LeetCode, beats 19% of the submissions in terms of runtime and 86% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The link to the code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.